In this video, we're going to dive in a little bit deeper into reversibility, specifically with regard to heat transfer processes. So we're going to do that in this, in the context of this note sheet. So if you don't have this printed out, I would suggest hit pause for a second, print this out, because you're definitely going to need this as we go along. Okay, welcome back. If you have your note sheet in front of you, we'll get started. So the case that we're going to look at is this heat transfer where we have water and a refrigerant, R134A. Just a note, in real life, right, a reversible heat transfer process is one where the heat can go either way. And that can obviously only happen if the two bodies are at exactly the same temperature, right? There needs to be no temperature difference because heat cannot flow uphill. So the ideal process is one where there is no temperature difference. That obviously still doesn't allow us to have any heat transfer. So we can think of an infinitesimally small temperature difference as kind of our requirement. This would take an infinitely long time or an infinitely large area. So obviously, right, the thing that we'll keep coming back to with reversibility are these are limits. So these aren't things that actually practically can be achieved. We can't have any heat transfer if two things are at exactly the same temperature. So we're going to, we would need an infinitely large heat exchanger and infinitely long time. Those are things which obviously we don't have. But this is a good practical limit. It sets kind of the boundaries for our system. So we're considering the case that's pictured here. Let's take a second to just look at what's happening in this case. We have all of the properties for all of these different streams already labeled, so that we don't have to go back and do that. But what we have here is water flowing through, say, these dark gray tubes, and our refrigerant flowing around the outside, so it's going, along this kind of curvy path over the tubes. And heat is being exchanged between these two fluids. So if we look at the water, water is coming in, it's 100 degrees Celsius, the quality is 0, right? That means it's a liquid. And as it's going through these tubes, it's boiling. So the water is leaving with a quality of 1. The flip of that is happening with the R134A. So R134A is coming in, and it is coming in on this side of the heat exchanger at the top. It has a quality of 0, and it leaves with a quality of 1 on this side of the heat exchanger. So if we picture what's happening, let's start by using the water as our control volume and calculate the heat leaving the water or entering the water from the R134A. So our enthalpy for this heat exchanger, we're going to skip the simplification step. We'll use this subscript W to mean water. And this is our, right, W is going to mean water. R is going to be our subscript for R134A, for our refrigerant. Our overall enthalpy is going to be m dot W H2 minus H1. That equals the heat transfer into our water. And we can simply add our numbers to that. So 0.01 kilograms per second. That's our mass flow rate. And we have our enthalpies, 2676.05 kilojoules per kilogram minus 419.02. That is units of kilojoules per kilogram. So our heat transfer, if we go through and do the math, is 22.570 kilojoules per second or kilowatts. We can calculate the rate of entropy change. So we have our entropy in and out. the total rate of entropy change, capital S, of our water is equal to the mass flow rate times the specific entropy change, lowercase s2 minus s1. So that would be equal to 0.01 kilograms per second times our entropies. So that's 7.3548 minus 1.3068. And that has units of kilojoules per kilogram Kelvin. Again, we can do the math and we get that the total rate of entropy change of the water is equal to 0.06048 kilojoules per Kelvin per second, or kilowatts per Kelvin. So that's our entropy change. This is equal to Q dot of the water. All right, fairly straightforward. We can use the, again, use the water as our control volume. And we can also use the, we can calculate the heat transfer using the change in specific entropy. So recall, for a reversible process, which this is, Q equals the integral of T ds. So if T is a constant, we call that isothermal, then T would just come out of the integral and Q equals T delta S. Or Q dot equals T delta S dot. So Q dot equals T delta S dot, which is equal to 100 degrees Celsius. And this is where things get a little bit tricky. We can't work in Celsius. We have to work in Kelvin. Times 0.0, what was our number? 0.06048. And that's kilowatts per Kelvin. We have to work in absolute temperature when we're working with entropy, and we have to do that because otherwise we can get negative numbers, right? Because 0 Celsius is kind of just this arbitrarily defined thing, so we wouldn't want this equation to have a sign change at 0 Celsius because we just picked, right? 0 Celsius is just an arbitrarily defined value. It happens to be the freezing point of water. If we were working in the Fahrenheit scale, 0 degrees Fahrenheit is the freezing point of salt water, which is, again, just an arbitrarily defined thing. So we don't want to have a sign change at 0. So we work in absolute temperature so that 0 isn't a sign change, it's absolute 0. If we go through and do this math, we find that Q dot is equal to 22.57 kilowatts, right? Which is exactly the same answer as what we got from our energy balance. And it's exactly the same answer. It's just two ways of looking at the exact same problem. We can do the energy balance, or we can look at entropy and calculate heat directly from entropy. Right? These things are all essentially equivalent, just different ways of looking at the same problem. If we wanted to figure out the mass flow rate of R134A, we can do our energy balance for the refrigerant. Right, it's going to look the same. And we know that the heat from the refrigerant is the same magnitude but the opposite sign of the heat from the water, right? Heat is going into the water, it's going out of the refrigerant, so they're the same magnitude, just different sign. So again, if we put some numbers to this, the mass flow rate of our refrigerant equals H4 minus H3 equals minus 22.57 kilowatts, which is minus, I guess I should put some subscripts up here. So this is QW, QW. This is just minus QW. We can put our values in for H3 and H4. If we look back up at our table, this is 374.74 minus 407.21, and those have units of kilojoules per kilogram. That equals minus 22.57 kilowatts or kilojoules per second, and we can calculate that the mass flow rate of our refrigerant is 0.695 kilograms per second. So one of the kind of interesting things that we see is that the amount of heat in each of these substances, right, they're both going through a phase change. They're both going through a phase change, but the amount of heat in that phase change is actually really different. So water boiling, it's a lot harder to get water to boil than it is to get this refrigerant to condense. So we have to use a lot more refrigerant, about 70 times as much as we have water for those heats to be, right, for this to be true, where the heat of the refrigerant is equal to the heat of the water. We can calculate the rate of entropy change, just like we did with the water. So delta S dot of our refrigerant is equal to the mass flow rate of our refrigerant times the change in entropy, S4 minus S3. And that equals 0.695 kilograms per second times 1.5228 minus 1.6098. And those units are kilojoules per kilogram Kelvin on entropy. And if we calculate this, our delta S for refrigerant equals minus 0.06048 kilowatts per Kelvin, which should look like a familiar number to us, right? This is exactly the same number, just an opposite sign as what we got for the rate of entropy change of the water stream. So if we calculate the rate of entropy change for the entire heat exchanger, right, delta S dot heat exchanger, that equals the rate of entropy change of the water plus the rate that the entropy of the refrigerant is changing, which equals, right, 0.06048 kilowatts per Kelvin minus 0.06048 kilowatts per Kelvin. So the rate of entropy change of the entire heat exchanger is equal to 0, or we could say that the rate of entropy change of the universe is equal to 0, which is what we mean for the fact that it's a reversible process. So individual components of the heat exchanger can have entropy going up. An individual component could have entropy going down, but the entropy change of the universe, because it's a reversible process, is still equal to 0. Hopefully this explains or helps you think about a little bit what we mean by a reversible process and specifically a reversible heat exchange. Right, a reversible heat exchange, if we think of temperature on this axis, if we have T1 and T2, Q flows that way. Delta S would be equal to 0, so this would be not reversible. And if we have, for instance, T1 and T2, then Q could go either way, which is reversible. And the smaller this temperature delta T, the smaller that temperature difference is, the closer for a heat exchange, the closer we're going to be to this ideal case where we would have a reversible heat exchange.